One of the most mind-bending questions in modern cosmology is, what happened before the Big Bang? For many, the Big Bang marks the beginning of everything: space, time, matter, and energy. But what existed, if anything, before this event? Was there a before, or was the Big Bang the true beginning of time itself? And if there was a time before the Big Bang, what did it look like? In this chapter, we'll explore the concept of nothing before the Big Bang, diving into the mysteries of what it means for time and space to be born. We will tackle the limits of human understanding, where the conventional laws of physics break down, and discuss how cosmologists have attempted to answer one of the most profound questions in science. Time and space, the Big Bang as the beginning. The prevailing theory in cosmology is that the Big Bang was not just the origin of matter and energy, but also the beginning of time itself. According to general relativity, space and time are interwoven in a single fabric known as space-time. This means that time itself is tied to the structure of the universe and its expansion. Before the Big Bang, there was no time in the conventional sense. The universe began from a singularity, a point where both space and time were infinitely dense and curved. In this state, the usual laws of physics, as we understand them, cease to function. The equations of general relativity break down, and what happened before or beyond this point is essentially unknown. In this sense, the Big Bang isn't just an explosion in space, it's the creation of space and time. When we ask what happened before the Big Bang, we are running into an intellectual paradox. The question itself assumes the existence of time before time began, but by the very nature of the Big Bang, time and space themselves began at this moment. What does nothing really mean? When we ask about the existence of nothing before the Big Bang, we need to clarify what we mean by nothing. In everyday life, we might think of nothing as an empty void, a place where there is no matter, energy, or anything at all. But in the context of cosmology, nothing is far more complicated. True nothingness, in the sense of a complete absence of space, time, and physical laws, is something we can't fully comprehend with our current understanding of physics. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, has challenged our conventional understanding of nothingness. At the quantum level, particles can pop in and out of existence due to quantum fluctuations, creating what might be described as nothing, but is still teeming with potential for particle creation. In this way, what we think of as nothing may still have a quantum field filled with energy and uncertainty. So when we talk about the state before the Big Bang, we're not necessarily talking about a place where there was nothing in the conventional sense. Instead, we might be referring to a state where space-time itself was compressed, or where quantum fields existed in a form we can barely understand, but without the distinct concepts of time, space, or matter as we know them. The problem with before the Big Bang, one of the challenges in considering what happened before the Big Bang, is the concept of time itself. In general relativity, time is inseparable from space. The two form the fabric of space-time. As the universe expands, so does time. But if the Big Bang represents the beginning of the universe, it also marks the beginning of time itself. The first moment of the Big Bang, often referred to as T equals 0, signifies the point where time and space come into being. This raises the question, if time itself began at the Big Bang, can we really talk about a time before it? If time didn't exist, then asking what happened before becomes a meaningless question. It's as if we're trying to describe a place outside of time, something our minds and language simply cannot grasp. In essence, when we look at the beginning of the universe, we encounter a limit to human knowledge, where our understanding of physics and time breaks down. To talk about before the Big Bang is, in many ways, to ask about something that lies beyond the scope of current scientific models and concepts. Quantum gravity, bridging the gap between time and space. If time truly began at the Big Bang, how can we understand the origins of the universe? This is where the theory of quantum gravity comes into play. Quantum gravity is a field of theoretical physics that attempts to reconcile the principles of quantum mechanics, which governs the behavior of particles, with general relativity, which describes gravity and the structure of space-time. Currently, we do not have a complete theory of quantum gravity, but some approaches, such as string theory and loop quantum gravity, propose that space-time itself may have a quantum structure at the smallest scales. In these models, space-time may not be a smooth, continuous fabric, but instead may be discrete, with the fabric of space and time made up of quantum loops or vibrating strings. According to some versions of quantum gravity, the Big Bang may not have been a sudden beginning, but rather the transition from one phase of the universe to another. For instance, some models suggest that the universe could have gone through cycles of contraction and expansion, a process referred to as the cyclic model. In this view, the Big Bang wasn't the first event, but the most recent one in a series of cosmic cycles, theories on what came before the Big Bang. While the Big Bang marks the beginning of time and space as we know it, there are several theories about what might have existed before it. While none of these theories are proven, they offer fascinating possibilities for what could have happened before the birth of the universe. 1. The cyclic model. This theory proposes that the universe goes through an endless series of cycles, each beginning with a Big Bang and ending with a big crunch, where the universe collapses back in on itself. In this view, the universe has no true beginning or end, but rather experiences a continuous cycle of birth, death, and rebirth. 2. The multiverse theory. Another possibility is that our universe is just one of many in a multiverse, a collection of multiple universes that exist simultaneously but are separate from one another. In this model, our universe could have emerged from a previous universe or from a bubble in a larger multiverse. The idea of a multiverse implies that the Big Bang may have been just one event in an ongoing process of creation, with other universes existing in parallel. 3. Quantum gravity and the no-boundary proposal. Some cosmologists, like Stephen Hawking, have proposed that the universe may not have had a traditional beginning. According to the no-boundary proposal, time itself may be a closed loop that has no beginning or end. In this view, the Big Bang wasn't a singular starting point, but rather a transition from a previous quantum state, with the universe emerging naturally from nothing in a way that doesn't require a traditional cause and effect explanation. 4. A pre-Big Bang universe. Some models suggest that the universe existed in some form before the Big Bang, in a state that we simply don't yet understand. These models propose that the universe could have been in a quasi-stable state, existing in a form where time as we know it didn't exist, and only the quantum potential for the universe existed. Conclusion: the limits of understanding. The question of what came before the Big Bang, or even whether before the Big Bang is a meaningful concept, pushes the boundaries of human knowledge. As we explore the unknown regions of cosmology, we encounter limitations, gaps in our understanding where current theories in physics break down. The origin of the universe is tied to the very fabric of time and space, and it may be a question that is forever beyond our ability to answer fully. While we may never fully understand the true nature of nothingness or what preceded the Big Bang, the ongoing search for answers continues to drive scientific inquiry and philosophical exploration. As we develop new theories and improve our observational tools, we may uncover new insights into the birth of the cosmos, and perhaps one day answer the question of what came before. As we continue our exploration into the question of whether anything existed before the Big Bang, it is essential to understand what the Big Bang itself truly represents. Far more than just an explosion, the Big Bang marks the birth of space and time, the origin of the universe as we know it. It is the event that gave rise to the space-time fabric that governs the laws of physics, matter, and energy. But how do we understand the Big Bang? And what does it mean for our conception of nothingness before this event? In this chapter, we will delve into the nature of the Big Bang, how it led to the creation of the universe, and the idea of space-time itself emerging from a state of singularity. We will also explore the role of quantum fluctuations and cosmic inflation, which help set the stage for the creation of our observable universe. The Big Bang, a beginning of space and time. The Big Bang is not an explosion in space, as it's often portrayed in popular media. Rather, it's the beginning of space-time itself. At the moment of the Big Bang, the entire universe, along with all of space and time, was contained in an incredibly hot, dense state. The Big Bang doesn't imply that space exploded into an already existing void. Instead, space itself began to expand, along with time. In this early state, the universe was compressed into a singularity, a point of infinite density and zero volume. At this point, the laws of classical physics, including Newtonian mechanics and even general relativity, break down. The idea of a singularity is difficult to grasp as it defies our intuitive understanding of matter and energy. The concept of infinite density implies that matter was packed together in such a way that it could not be compressed further, and at this stage, time and space were not yet distinct from one another. The singularity represents the boundary between what we can understand with our current theories and the unknown. The moment before the Big Bang, in the conventional sense, simply cannot be described using our present laws of physics. As we move forward in time from the Big Bang, we encounter a universe that gradually evolves, but the origin of space and time remains a mystery that scientists are still trying to solve. Quantum mechanics and the birth of the universe. To understand the Big Bang and the birth of space-time, we must incorporate the principles of quantum mechanics. At the most fundamental level, the universe operates according to quantum laws, which govern the behavior of particles and forces at microscopic scales. Quantum mechanics allows for phenomena that seem impossible in the classical world, such as particles existing in multiple states at once or being in two places at the same time. These strange behaviors arise because of quantum fluctuations, temporary changes in energy levels that occur in empty space. The early universe, at the time of the Big Bang, was governed by quantum fluctuations on an extremely small scale. These fluctuations created the seed for the structure of the universe, influencing the formation of galaxies and cosmic structures. Quantum mechanics explains how, from a singularity, the universe began to evolve and expand. It also provides a framework for understanding the uncertainty inherent in the universe, where particles could spontaneously emerge from a quantum field and disappear just as quickly. The quantum fluctuations that occurred in the very first moments of the universe are key to understanding how the large-scale structures we see today emerged. They were the fluctuations that shaped the density variations in the early universe, which eventually led to the formation of galaxies, stars, and other cosmic objects. Cosmic inflation, the exponential expansion of space-time. To truly understand how the universe evolved from the initial singularity, we must turn our attention to the theory of cosmic inflation. This theory was proposed in the early 1980s by physicist Alan Guth and suggests that, in the first fraction of a second after the Big Bang, the universe expanded at an exponentially fast rate, far faster than the speed of light. Inflation is thought to have been driven by a form of energy that permeated space, causing space itself to expand by an enormous factor in a fraction of a second. During this inflationary period, the universe increased in size by a factor of 10^26 in just 10^32 seconds. This rapid expansion explains several key features of the universe, including its uniformity and the large-scale structure of galaxies. Without inflation, the universe would not be as homogeneous as we see it today, with galaxies and galaxy clusters distributed in a cosmic web. The theory of inflation also solves several long-standing problems in cosmology, such as the horizon problem, why the universe appears uniform despite being so large, and the flatness problem, why the universe appears to be so finely tuned. The rapid expansion of the universe during inflation essentially smoothed out any variations, creating the homogeneous and isotropic universe we observe today. One of the most fascinating aspects of inflation is that it allows for the possibility of eternal inflation. In this scenario, inflation doesn't just occur once, it continues indefinitely, with new regions of space constantly being created in a multiverse of infinite universes. Each of these universes could have different physical laws, constants, and properties, potentially giving rise to entirely different kinds of cosmic environments. The emergence of matter and energy. After the initial burst of inflation, the universe continued to expand, but at a much slower rate. As it expanded, it cooled, allowing particles to form and interact. Within the first few minutes of the Big Bang, the universe was filled with a hot soup of quarks, gluons, electrons, and photons. These elementary particles began to combine to form protons and neutrons, the building blocks of atomic nuclei. During the first few minutes, the universe went through a process called nucleosynthesis, in which protons and neutrons combined to form light atomic nuclei, such as hydrogen, helium, and traces of lithium. This period of rapid particle formation laid the foundation for the creation of atoms, which would later come together to form stars, galaxies, and the matter we see today. The universe continued to cool and expand, and after about 380,000 years, atoms began to form as electrons, combined with atomic nuclei to create neutral atoms. This event is called recombination, and it marks the point at which the universe became transparent to light. Prior to recombination, the universe was a hot, opaque plasma where light could not travel freely. After recombination, the universe became transparent, and light could finally travel freely, leading to the release of the cosmic microwave background radiation, CMB, a faint glow left over from the early universe. The CMB is a key piece of evidence for the Big Bang theory and provides a snapshot of the universe at the time of recombination. By studying the CMB, scientists can learn about the conditions of the early universe and trace the origins of galaxies, stars, and large-scale structures. The birth of stars and galaxies. As the universe continued to expand and cool, matter began to clump together due to the force of gravity, forming the first dark matter halos and galaxies. These early galaxies were much smaller and less structured than those we observe today, but over billions of years they merged and grew into the galaxies we know today. The formation of stars and galaxies was a slow process. The gas in the universe cooled and condensed into clumps, and within these clumps, gravity caused matter to collapse inward, leading to the birth of the first stars. These stars were different from modern stars in many ways. They were much more massive and short-lived, burning through their fuel quickly and ending their lives in supernova explosions. These early stars were the first to begin fusing hydrogen into helium, producing heavier elements in the process. The explosions of these first stars enriched the surrounding gas with heavier elements, laying the foundation for the formation of future generations of stars and planets. As galaxies formed and grew, they began to interact with each other, leading to the creation of larger structures such as galaxy clusters and the cosmic web we see today. The ongoing evolution of the universe. The universe has continued to evolve since the Big Bang, with galaxies merging, stars forming, and new structures emerging. However, the expansion of space is ongoing, and the universe is still evolving today. It continues to cool, and stars and galaxies continue to form in new regions of space. However, the process of cosmic expansion means that distant galaxies are moving farther away from us, and over time, the rate of expansion will continue to increase due to dark energy. As we look deeper into the cosmos, we are able to see further back in time. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope allow us to observe galaxies and stars that formed just a few 100 million years after the Big Bang, providing a window into the early universe and helping to answer questions about the origins of space, time, and matter. Conclusion: the beginning of everything. The Big Bang marks the beginning of the universe, space, time, and all, the forces that govern the cosmos. From the earliest moments of cosmic inflation to the formation of the first stars and galaxies, the Big Bang set the stage for the universe's evolution. While the questions of what existed before the Big Bang remain largely unanswered, the discovery of the Big Bang has revolutionized our understanding of the cosmos and the fundamental forces that shape it. The exploration of the universe's origins continues to inspire and challenge scientists, philosophers, and cosmologists as they attempt to understand the true nature of time, space, and matter. The mysteries of the Big Bang remain at the forefront of our search for knowledge, and as we look further into the universe, we continue to learn more about the incredible processes that shaped our existence. To truly understand the origins of the universe, we must venture into the realm of quantum mechanics, the branch of physics that deals with the strange and often counterintuitive behavior of particles at the smallest scales. While the Big Bang represents the beginning of space and time, quantum mechanics helps explain how the universe could have emerged from nothing, or from a state where the usual laws of physics do not apply. Quantum mechanics challenges our conventional notions of reality and causality. It operates in a realm where particles behave unpredictably and can exist in multiple states at once. Understanding these principles is essential if we want to comprehend the birth of the universe, an event where the usual rules of time and space were first set into motion. In this chapter, we will explore how quantum mechanics plays a crucial role in the origin of the universe, especially in the context of the Big Bang. We'll look at quantum fluctuations, the idea of quantum vacuum, and how space-time itself might have originated from quantum processes leading to the creation of the cosmos. Quantum fluctuations, the birth of space-time. One of the most important concepts in quantum mechanics is quantum fluctuations. These are temporary changes in energy that occur even in a vacuum, empty space. These fluctuations cause particles and antiparticles to appear and disappear spontaneously, creating what we might call pockets of energy that momentarily exist before vanishing. In the early universe, quantum fluctuations were far more significant than they are today. In fact, it is believed that these fluctuations played a key role in the formation of the universe. According to the quantum fluctuation model of the Big Bang, the universe could have originated from a quantum fluctuation in a vacuum state, a state of nothingness where the usual laws of physics break down. This idea suggests that, in the very beginning, the universe might have appeared as a small quantum fluctuation, a minute, incredibly dense point that eventually grew into the universe we see today. The vacuum state from which the Big Bang arose could have been filled with a kind of quantum potential for the creation of space-time itself. This idea of a quantum vacuum lays the foundation for understanding how something can come from nothing in the quantum world. The quantum vacuum, space-time from nothing. To grasp the quantum origin of the universe, we need to understand the concept of a quantum vacuum. In classical physics, a vacuum is simply empty space, devoid of matter and energy. However, in quantum mechanics, even empty space is far from empty. According to the Heisenberg uncertainty principle, there are inherent uncertainties in the energy of a system, even when no particles are present. This leads to the idea of a quantum vacuum, a space filled with quantum fluctuations, virtual particles, and energy. The quantum vacuum is not just empty space, it is a dynamic field that can produce energy and particles through fluctuations. This means that space itself can spontaneously fluctuate and produce particles that briefly come into existence before disappearing. These fluctuations are governed by the principles of quantum mechanics and are thought to have played a crucial role in the early moments of the universe's existence. In fact, some physicists propose that the Big Bang itself could have been the result of a quantum fluctuation in this vacuum. According to the quantum creation model, the universe emerged from a state of pure quantum potential where space and time did not yet exist in the way we understand them today. The Big Bang could have been the creation of both space-time and matter from this quantum fluctuation. The role of inflation in the early universe. To understand how the universe evolved from this quantum fluctuation, we turn to the theory of cosmic inflation. As mentioned earlier, inflation refers to a period of rapid exponential expansion that occurred in the first moments after the Big Bang. During this brief period, lasting less than a fraction of a second, the universe expanded by an enormous factor stretching from a subatomic size to a vast expanse. Inflation is thought to be driven by a form of energy, often referred to as the inflaton field, which existed in the early universe. This field was responsible for the dramatic expansion of space-time, smoothing out any irregularities and setting the stage for the universe we see today. Inflation explains why the universe appears so uniform on large scales and why distant parts of the cosmos seem to have similar properties. From a quantum perspective, the inflaton field itself could be seen as a quantum field, a field with its own quantum fluctuations. These fluctuations in the field were responsible for the density variations that eventually led to the formation of galaxies, stars, and the large-scale structure of the universe. In this sense, quantum fluctuations during the inflationary period acted as the seeds for the clumpy structure of the universe that we observe today. Time and space in the early universe. In the first moments of the Big Bang, space and time were not separate entities as we understand them now. Instead, they were part of a unified quantum state. The theory of general relativity suggests that time and space are deeply interconnected, forming the fabric of space-time. However, this theory breaks down at extremely small scales, near the Planck length, where the effects of quantum mechanics become significant. In the early universe, as space-time began to form, quantum mechanics played a critical role in shaping the structure of the cosmos. The universe was initially in a quantum superposition, meaning that particles and energy existed in multiple states simultaneously, and only as the universe began to expand did these states collapse into the familiar forms we observe today. During this early phase, quantum fluctuations were embedded in the very structure of space-time, influencing how the universe evolved. At this stage, the universe was also governed by a theory of quantum gravity, a yet-to-be-developed theory that would merge quantum mechanics with the effects of gravity. Quantum gravity is essential for understanding the very early universe because it would explain how space-time itself can be quantized and behave according to quantum laws. Theories like string theory and loop quantum gravity attempt to unify gravity with the quantum realm, but a complete theory of quantum gravity is still beyond our reach. The Planck era, the birth of spacetime. The first moments of the universe, known as the Planck era, occurred within 10 to 43 seconds after the Big Bang. This is the time when the universe was smaller than an atom and incredibly dense. During this period, all four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were believed to be unified into a single force. At the Planck scale, both quantum mechanics and gravity were inextricably linked, but we currently lack a theory that can fully describe this quantum gravity regime. The quantum fluctuations and uncertainty of this era are thought to have created the seeds of the universe's structure, providing the initial fluctuations in density that would later evolve into stars and galaxies. The universe during the Planck era was governed by the laws of quantum mechanics, but gravity played a role at a level that we don't fully understand. Once the universe began to expand during inflation, gravity and quantum mechanics began to decouple, leading to the universe's growth into the familiar space-time we can measure today. Understanding the limits of before. As we explore the quantum nature of the universe, we return to the question of what came before the Big Bang. Quantum mechanics suggests that there may not have been a before in the traditional sense. The universe could have always existed in a quantum state with no clear beginning or end. This challenges our classical understanding of time and space, which assumes that the universe must have had a start. In some versions of quantum cosmology, the idea of a quantum state before the Big Bang suggests that the universe may have been in a cyclic or eternal process of creation. This model proposes that the universe goes through endless cycles of big bangs and big crunches, with no true beginning or end. According to this view, the Big Bang was just the latest phase in an ongoing cycle of expansion and contraction. Conclusion: the quantum origins of the universe. The birth of the universe from a quantum fluctuation represents one of the most fascinating and mind-boggling aspects of cosmology. The theory that quantum mechanics played a role in the creation of the cosmos challenges our understanding of time, space, and reality. The interplay between quantum fluctuations, cosmic inflation, and general relativity shaped the universe into what it is today. While we may never fully understand how the universe emerged from a quantum state of nothingness, the continued study of quantum mechanics, quantum gravity, and cosmology will provide deeper insights into the origins of space-time. The mysteries of the Big Bang and the nature of the universe's birth continue to inspire scientists and philosophers alike, driving humanity to explore the deepest corners of existence. When we consider the state before the Big Bang, we often envision a void, an emptiness where nothing exists, not even time or space. But is this concept of nothing truly possible? In the realm of cosmology, the idea of absolute nothingness is a philosophical paradox as much as a scientific one. In this chapter, we will delve into the concept of nothing from the perspective of cosmology, examining how modern physics challenges the traditional idea of an empty void and whether we can even conceive of a state where no space, time, or matter exists. To understand this, we must first examine what we mean by nothing in both everyday language and scientific terms. Are we talking about a vacuum, a space devoid of matter, or is there something more profound, something that defies our understanding of existence? What does nothing mean in everyday terms? In everyday language, we tend to think of nothing as the absence of matter, energy, or any kind of structure. We imagine an empty void, a place where there is no air, no stars, no particles, and no space. This absence can be difficult to conceptualize, as we are used to seeing something everywhere we look. For example, when we speak of the vacuum of space, we think of it as empty, a vast expanse with no matter between stars and galaxies. However, even in these voids, there is still something present: dark matter, cosmic radiation, and even quantum fluctuations. In other words, even what we consider empty space is not truly empty at all. In quantum mechanics, the concept of nothing is even more complex. The vacuum, while devoid of particles, is still a place of constant quantum activity, where particles can spontaneously pop in and out of existence. This quantum vacuum is not truly empty, but instead teeming with potential energy, even in the absence of traditional matter. Nothing in the context of physics, the vacuum state. In the language of physics, nothing is often described as a vacuum, a region of space where there are no particles, no light, and no energy. But even in the vacuum of space, there are still fields and energy fluctuations. These fields, such as the electromagnetic field, permeate all of space, and their fluctuations give rise to phenomena like virtual particles, which pop into existence and then vanish just as quickly. This leads us to a surprising conclusion. Even the concept of empty space may not be a true void. Instead, what we consider empty could be filled with quantum fields that fluctuate in energy, creating a dynamic vacuum state. This idea is central to quantum field theory and quantum mechanics, where the vacuum is not a blank space, but a complex structure of energy and fluctuating fields. In fact, physicists suggest that the vacuum state of the universe might have been the birthplace of everything we observe today. The universe, according to some models, could have emerged from a quantum fluctuation in this empty vacuum, leading to the creation of both space and time in the Big Bang. Can nothing really exist? To dive deeper into the idea of nothing, we must ask, can true nothingness exist at all? The very concept of nothing, where there is no matter, no space, no time, appears to conflict with our current understanding of the universe. Modern physics suggests that even in the absence of matter, there is still something: energy, fields, and vacuum fluctuations. At the quantum level, these fluctuations occur everywhere, even in what we think of as empty space. The notion of true nothingness is further complicated by the cosmological principle, which assumes that the universe is uniform and isotropic, meaning it looks the same in every direction. If the universe had a true beginning, and it began as an expanding point of energy, then there would have been a state before this expansion where space-time itself didn't exist as we know it. But if there were no space or time, can we even talk about a state before the Big Bang? Was there no before at all? Some scientists propose that the universe emerged from a quantum vacuum fluctuation, a spontaneous creation of space and time, suggesting that the universe might have come from nothing in the quantum sense. In this view, the nothing that existed before the Big Bang wasn't an empty void, but instead a quantum state with the potential to create the universe we see today. This challenges our intuitive understanding of nothingness, showing that what we think of as empty space is, in reality, full of energy, uncertainty, and potential. The birth of space-time. What came before the Big Bang? As we explore what came before the Big Bang, we must confront the issue of time itself. If the Big Bang represents the beginning of time, then asking what happened before the Big Bang might be a nonsensical question. Time, as we understand it, didn't exist before the Big Bang. Instead, it began with the Big Bang, along with the creation of space. The idea that time itself began at the Big Bang is a fundamental concept in modern cosmology. In Einstein's theory of general relativity, time is intimately connected to space, forming the fabric of space-time. Before the Big Bang, there was no space-time as we understand it, meaning that the usual notions of time don't apply. There is no before in the way we think about time. This idea is known as the no-boundary proposal, which suggests that the universe had no beginning or end, but rather existed in a quantum state that evolved into our observable universe. In this view, the Big Bang wasn't the start of a timeline. It was the emergence of space-time itself from a quantum fluctuation, with time as we know it beginning only with the onset of the Big Bang. The quantum creation of the universe. According to some models, including quantum cosmology, the universe could have emerged from quantum fluctuations in a pre-existing quantum field. These fluctuations are thought to have created the very fabric of space-time that we experience today. The inflationary model of the Big Bang provides one possible explanation for this process. During the brief moments after the Big Bang, the universe expanded exponentially due to inflation driven by a quantum field. In the quantum view, the universe may have come from a state of potential where the laws of quantum mechanics allowed for the creation of space-time itself. Instead of thinking of the universe as emerging from nothing, we could think of it as emerging from a quantum vacuum, a state that is not truly empty but filled with energy and potential for creating reality. Some theorists also suggest that the universe is the result of eternal inflation, a process in which the universe continuously generates new pocket universes from a fluctuating quantum field. In this view, the multiverse is born out of a quantum vacuum that perpetually gives rise to new universes, each with its own laws of physics and initial conditions. Our universe, then, could be one of many, each emerging from quantum fluctuations in an eternally expanding cosmic sea. Is nothing truly possible? The idea of nothing in cosmology raises questions that go beyond physics and into the realm of philosophy. If nothing truly means an absence of space, time, and matter, is it even a concept we can understand? Our current understanding of quantum mechanics and cosmology suggests that there is no such thing as a true nothing. Even the vacuum of space is not empty, but is filled with quantum fields and energy fluctuations that could give rise to particles, energy, and even entire universes. In a sense, the universe itself may have emerged from a quantum state, where the distinction between nothing and something becomes meaningless. What we consider to be nothing is actually a quantum state filled with potential energy, which can give rise to space, time, and matter. The universe, then, may have come into existence not from absolute nothingness, but from a state that we cannot yet fully comprehend, a quantum vacuum that was teeming with possibilities. Conclusion: the paradox of nothingness. The question of whether nothing existed before the Big Bang is a paradox that challenges our understanding of space, time, and existence itself. In the realm of cosmology, nothing is not a simple void, but is instead a state filled with energy, potential, and quantum fields. The universe may have emerged not from an empty void, but from a quantum fluctuation in a quantum vacuum, a state where the laws of physics could create the cosmos we observe today. As we continue to explore the origins of the universe and the nature of space-time, we are faced with the limits of human knowledge and the mysterious nature of existence. While we may never fully grasp the true nature of nothingness, the exploration of these ideas challenges our understanding of reality and pushes the boundaries of science and philosophy. In the search for answers to the origin of the universe, many scientists and cosmologists have proposed models that challenge the traditional understanding of the Big Bang as the beginning of everything. One of the most intriguing ideas is the cyclic universe theory, the notion that the universe is not a singular event, but part of an endless cycle of expansion and contraction, of big bangs and big crunches. Could the Big Bang that we observe be just one of an infinite series of cycles, each with its own cosmic rebirth? Could the universe have been going through these cycles for eternity, with no true beginning or end? In this chapter, we will explore the idea of a cyclic universe, the evidence supporting it, and how it reshapes our understanding of time, space, and the cosmos. The cyclic universe. Theory. The concept of a cyclic universe, sometimes referred to as the oscillating universe, dates back to ancient cosmological ideas, where many cultures and philosophies imagined a cyclical nature of the cosmos. However, the modern interpretation of a cyclic universe emerged from the work of several physicists in the 20th century, including Albert Einstein and Roger Penrose. The basic idea behind the cyclic model is that the universe undergoes an endless sequence of cycles, each beginning with a big bang and ending with a big crunch, only to be followed by another big bang. In this scenario, the universe continually expands and contracts over infinite time, never truly reaching a final end. This idea contrasts with the more traditional understanding that the universe had a single Big Bang and will eventually decay into an irreversible state, such as in the case of the Big Freeze or the Big Rip. In a cyclic universe, the expansion of space during the Big Bang is followed by a contraction as gravity eventually overcomes the forces driving the universe's expansion. This contraction leads to a big crunch, in which the universe collapses back into a singularity, much like the state it was in before the Big Bang. From this singularity, another Big Bang would occur, restarting the cycle. The role of dark energy in a cyclic universe. One of the key challenges to the cyclic universe theory is understanding how dark energy, responsible for the accelerated expansion of the universe, fits into this model. Dark energy is a mysterious force that makes up about 68% of the universe and is thought to be driving the expansion of space at an ever-increasing rate. In a standard cyclic model, it's difficult to imagine how dark energy could reverse itself to cause the contraction of the universe. If the universe continues expanding at an accelerated rate due to dark energy, the idea of a big crunch, a collapse of the universe, seems improbable. However, some theorists have proposed that dark energy might change over time or even reverse in the far future, allowing the universe to contract. One such idea involves the nature of quintessence, a hypothetical form of dark energy that could evolve over time and potentially allow for a cyclic universe. If dark energy does evolve, or if its influence weakens in the future, the universe could reach a point where gravity begins to dominate once again. This could lead to a contraction, ultimately culminating in a big crunch and restarting the cycle. The ekpyrotic universe. A twist on the cyclic model. A more recent variation of the cyclic universe theory is the ekpyrotic universe model, proposed by cosmologists Paul Steinhardt and Neil Turok in the early 2000s. In this model, the universe doesn't go through a cycle of big bangs and big crunches due to the expansion and contraction of the same universe. Instead, it suggests that the universe is part of a higher dimensional space, where the bang is caused by the collision of two three-dimensional membranes, within a higher dimensional space. In the ekpyrotic universe theory, our universe is one of two parallel branes floating in a higher dimensional space. These branes occasionally collide, leading to a big bang that marks the beginning of a new cycle. The collision causes a release of energy, creating the universe's matter and space-time. After each collision, the universe expands, and eventually the brains may separate, setting the stage for another collision and another Big Bang. This model removes the need for a big crunch and instead focuses on higher dimensional physics to explain the cyclical nature of the universe. It challenges our conventional understanding of the cosmos and suggests that the universe's origins could be linked to the dynamics of extra dimensions. The evidence for a cyclic universe. While the idea of a cyclic universe remains speculative, there are some theoretical and observational clues that suggest the universe may be cyclical in nature. Some of the evidence for this includes the cosmic microwave background, CMB. The cosmic microwave background, CMB radiation, a faint afterglow of the Big Bang, holds important clues about the early universe. The CMB provides a snapshot of the universe when it was just 380,000 years old, offering valuable insight into its temperature, density, and structure at that time. Some researchers have proposed that certain features in the CMB, such as specific temperature fluctuations or imprints left by gravitational waves, could be the remnants of previous cycles of the universe. If the universe had gone through multiple cycles of expansion and contraction, these echoes might be visible in the CMB, potentially revealing the memory of past universes. However, this evidence is still debated, and many scientists argue that the imprints detected in the CMB could simply be the result of inflation during the early universe rather than the remains of previous cycles. Black hole information paradox. The black hole information paradox is another theoretical challenge that has led some physicists to consider cyclic models of the universe. This paradox arises from the idea that when something falls into a black hole, the information about that object is lost to the outside universe. However, in quantum mechanics, information is never truly lost, and this creates a conflict with our understanding of physics. One potential resolution to this paradox is that information from evaporating black holes could be recycled through successive cycles of the universe. As each cycle progresses, the information trapped within black holes could be preserved, allowing it to pass into the next cycle of expansion and contraction. The role of entropy in a cyclic universe. In thermodynamics, entropy refers to the amount of disorder or randomness in a system. As the universe expands, entropy increases, meaning the universe becomes more disordered over time. According to the second law of thermodynamics, the total entropy of the universe will always increase, leading to a heat death scenario in which all processes cease. However, proponents of the cyclic universe model argue that entropy doesn't have to build up indefinitely. In some cyclic models, each new cycle starts with a low entropy state, allowing the universe to experience a new beginning of order. These models suggest that the Big Crunch could effectively reset the universe's entropy, leading to a fresh cycle in which new structures, stars, and galaxies can form. The multiverse and cyclic universes. The idea of a cyclic universe fits neatly into some models of the multiverse, which propose that our universe is just one of many in an infinite cosmic landscape. In a multiverse scenario, universes could undergo an eternal process of birth, evolution, and rebirth. Each universe could experience its own version of the Big Bang, followed by a period of expansion, contraction, and a return to a quantum state that sets the stage for a new Big Bang. This concept of the multiverse adds a layer of complexity to the cyclic universe theory, suggesting that the cycle of universes might not be confined to a single, isolated cosmos, but instead could involve an infinite series of universes, each one different from the last. The idea of eternal inflation, in which new pocket universes are constantly being created, ties the concept of a cyclic universe to the broader framework of the multiverse. Conclusion: an infinite cosmic cycle. The theory of a cyclic universe offers an intriguing possibility that the universe, instead of having a singular beginning and end, goes through an eternal series of cycles. This model provides a way to reconcile the Big Bang with ideas of eternal creation, where the universe is constantly being reborn from the ashes of the previous cycle. However, the cyclic model faces several challenges. The role of dark energy, the exact mechanisms behind cosmic inflation, and the nature of entropy all remain areas of active research and debate. Whether the universe will eventually collapse in a big crunch or continue expanding forever in a big freeze is still uncertain. Nevertheless, the idea of a cyclic universe opens up new possibilities for understanding the origin and future of the cosmos. As our understanding of cosmology continues to evolve, the cyclic universe theory provides one of the most fascinating alternatives to the traditional view of the universe's singular beginning. Whether we live in a universe that is constantly reborn or one that had a definite beginning, the search for answers to these questions continues to push the boundaries of science and our understanding of reality. As we continue exploring the profound mysteries surrounding the origin and fate of our universe, we encounter one of the most speculative and exciting ideas in modern cosmology: the multiverse theory. The multiverse suggests that our universe, with its billions of galaxies, stars, and planets, may be just one of many, each with its own distinct properties, physical laws, and dimensions. But what does it mean for our understanding of the cosmos if there are other universes beyond our own? Could there be infinite universes, each with its own unique set of conditions and perhaps even alternate versions of ourselves? In this chapter, we will explore the multiverse theory, the various models proposed to explain it, and the possible implications for our understanding of reality. What is the multiverse? The multiverse is the hypothetical collection of multiple universes, including the one we inhabit. Each universe within the multiverse may have its own set of physical laws, constants, and properties, which could differ from our universe in subtle or dramatic ways. In some versions of the multiverse theory, these universes could be entirely disconnected from each other, while in others, they could interact or even overlap. The idea of the multiverse has roots in various branches of theoretical physics, including quantum mechanics, cosmology, and string theory. While the concept may seem outlandish, some versions of the multiverse are consistent with our current understanding of physics and mathematics. While we have no direct evidence of other universes, the multiverse theory provides an intriguing framework for explaining some of the mysteries of the universe. The many worlds interpretation of quantum mechanics. One of the earliest and most well-known models of the multiverse comes from quantum mechanics, the field of physics that describes the behavior of particles at the smallest scales. The many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957, suggests that every quantum event could give rise to a new parallel universe. In the many worlds interpretation, when a quantum system exists in multiple possible states, such as an electron having different possible positions, the universe splits into different branches, each representing one of those possible outcomes. These different branches, or worlds, exist in parallel, each representing a different outcome of the quantum event. For example, consider the famous thought experiment known as the Schrödinger's cat paradox, where a cat in a box can be both alive and dead until the box is opened and observed. In the many worlds interpretation, when the box is opened, the universe splits into two separate worlds, one in which the cat is alive and another in which the cat is dead. Every time a quantum decision is made, the universe branches into different possibilities. This interpretation of quantum mechanics implies the existence of an infinite number of parallel universes, each representing a different outcome of every quantum event. While this model is fascinating and mathematically consistent, it raises questions about the nature of reality, the role of observation, and the very definition of a universe. The string theory and the landscape multiverse. Another version of the multiverse theory arises from string theory, a framework that aims to unify all fundamental forces of nature, including gravity, into a single theoretical framework. String theory proposes that the fundamental particles we observe are not point-like objects, but rather vibrating strings of energy. One of the key predictions of string theory is the existence of extra dimensions beyond the familiar three dimensions of space and one dimension of time. These extra dimensions could give rise to different physical laws depending on how the strings vibrate in these dimensions. In this view, our universe is just one of many possible solutions to the way the strings vibrate, each with its own set of physical properties. This idea leads to the concept of the landscape multiverse, which suggests that there could be an infinite number of universes, each with different physical laws and constants. The landscape refers to the vast number of possible configurations of the strings, each configuration corresponding to a different universe with distinct properties. Some of these universes might have the same laws of physics as our own, while others could have completely different laws, such as different values for the speed of light or the strength of gravity. While string theory offers a potential explanation for the multiverse, it remains highly speculative. String theory itself has not been experimentally verified, and the landscape multiverse is still a subject of active debate among physicists. However, the idea that our universe could be just one of many possible universes, each with different physical laws, is an exciting possibility that opens up new avenues for understanding the nature of the cosmos. Eternal inflation and the bubble multiverse. Another version of the multiverse theory comes from the idea of eternal inflation, a concept that builds upon the theory of cosmic inflation. As mentioned earlier, inflation suggests that in the first moments after the Big Bang, the universe expanded at an exponential rate, stretching from a subatomic size to a vast expanse. Eternal inflation extends this idea by suggesting that inflation did not stop after the Big Bang, but continues in certain regions of space. According to this model, while the observable universe is expanding at a slower rate, other regions of space are still undergoing eternal inflation, creating new pocket universes within the larger multiverse. Each pocket universe, or bubble universe, forms from a different region of the inflationary field, leading to a vast multiverse of universes with potentially different laws and properties. In the bubble multiverse, the process of inflation would have been triggered by a quantum fluctuation, causing regions of space to expand rapidly and become disconnected from one another. Each bubble universe would be a separate and independent entity, with its own set of physical laws and constants. Some of these universes may resemble our own, while others could be completely different, with different numbers of dimensions, laws of physics, and even types of matter. The bubble multiverse model provides a natural explanation for the vastness of the universe and the fine-tuning of the physical constants we observe. If there are infinitely many universes with different laws, it's not surprising that we happen to live in a universe with the conditions suitable for life. The mathematical multiverse. All possible universes exist. One of the most radical ideas within the multiverse theory comes from Max Tegmark, a physicist who proposed the idea of a mathematical multiverse. In his view, all mathematically possible universes exist, regardless of whether they are physically real in the way we understand reality. According to the mathematical multiverse hypothesis, every possible mathematical structure corresponds to a different universe. This means that any universe that can be described by a mathematical model, no matter how strange or unusual, actually exists in some form. In this view, the laws of physics are simply the mathematical rules that govern the behavior of each universe. This idea takes the concept of the multiverse to a philosophical extreme, suggesting that the very nature of reality is determined by mathematical structures. It also raises profound questions about the nature of existence itself. If all mathematically possible universes exist, what does this say about the nature of our own universe and the meaning of life? The search for evidence. Can we prove the multiverse? One of the most difficult challenges of the multiverse theory is that it is currently unobservable. By definition, universes beyond our own are disconnected from our observable universe, making it impossible to directly observe or measure them. As a result, the multiverse theory is inherently unfalsifiable. We have no way to directly test or prove the existence of other universes. However, some scientists are working on ways to indirectly test the multiverse theory. For example, some versions of the eternal inflation model predict that the collision of bubble universes could leave detectable imprints on the cosmic microwave background, CMB radiation. Similarly, certain properties of dark matter and dark energy might offer clues about the presence of other universes. Despite these challenges, the multiverse remains a fascinating and deeply speculative area of research. The idea that there could be an infinite number of universes, each with its own set of laws and properties, reshapes our understanding of reality and raises profound philosophical and scientific questions about the nature of existence. Conclusion: the infinite possibilities of the multiverse. The multiverse theory opens up a vast landscape of possibilities for the nature of reality. Whether it is the result of quantum fluctuations, the outcome of cosmic inflation, or the manifestation of mathematical structures, the idea that our universe is just one of many raises profound questions about the nature of existence. If the multiverse theory is correct, it could mean that the universe we observe is just one tiny part of a much larger cosmic tapestry filled with infinite possibilities. As we continue to explore the cosmos and push the boundaries of our understanding, the search for answers about the multiverse will undoubtedly remain one of the most exciting and thought-provoking areas of modern science. One of the most profound questions that humanity has asked throughout history is whether we are alone in the universe. Given the vastness of space, the sheer number of galaxies, and the countless planets orbiting stars, the possibility of extraterrestrial life seems almost inevitable. However, despite decades of searching, we have yet to find definitive evidence of alien life. So the question remains, are we truly alone? In this chapter, we will explore the search for extraterrestrial life, the methods scientists use to hunt for evidence, and the implications of discovering life beyond Earth. We will also consider the philosophical and existential questions that arise when we contemplate the possibility of life elsewhere in the universe. Could the discovery of alien life change our understanding of ourselves, or would it simply reinforce what we already know about our place in the cosmos? The Fermi paradox. Why haven't we found alien life? The search for extraterrestrial life is one of the most exciting and ambitious endeavors in modern science. Drake's equation, developed by astronomer Frank Drake in 1961, attempts to estimate the number of technologically advanced civilizations in our galaxy. Based on factors such as the rate of star formation and the number of planets that could potentially support life, the equation suggests that there could be millions of planets in the Milky Way galaxy alone that could harbor intelligent life. However, despite these optimistic predictions, the paradox remains. Why haven't we found evidence of extraterrestrial civilizations? This conundrum is known as the Fermi paradox, named after the famous physicist Enrico Fermi, who famously asked, "Where is everybody?" The question arises because, given the vast number of potentially habitable planets, it seems statistically likely that extraterrestrial life should exist, yet we have yet to detect any signs of it. One explanation for this paradox is that intelligent life may be incredibly rare or short-lived. Advanced civilizations may emerge only to self-destruct through war, environmental collapse, or technological failure before they have a chance to establish contact with other civilizations. This is sometimes referred to as the Great Filter, the idea that there is some kind of barrier or series of events that prevent intelligent life from emerging or surviving for long periods of time. Another possible explanation is that extraterrestrial civilizations may be intentionally avoiding us or are simply too far away for us to detect. Advanced alien civilizations might be using technologies that are undetectable to our current instruments, or they may deliberately refrain from making contact, adhering to a policy similar to our own Prime Directive, the idea that advanced civilizations should avoid interfering with less developed societies. The search for microbial life, Mars and beyond. While the search for intelligent extraterrestrial civilizations continues, many scientists focus on the more attainable goal of finding microbial life. Microbial life, such as bacteria or simple organisms, is far more likely to exist on other planets than complex life forms, making it the primary target of current research. The planet that has received the most attention in this search is Mars. Mars is the most Earth-like planet. in our solar system, with evidence of ancient river valleys, lake beds, and polar ice caps suggesting that it may have once had liquid water on its surface, one of the key ingredients for life. In the past few decades, robotic missions to Mars, including the Curiosity rover, Opportunity rover, and Perseverance rover, have been exploring the planet's surface in search of signs of past or present life. NASA's Perseverance rover, which landed on Mars in 2021, is specifically tasked with looking for biosignatures, chemical evidence that could indicate life. The rover is also collecting soil samples that will eventually be returned to Earth for analysis. Scientists are particularly interested in ancient sedimentary rocks on Mars, which may have preserved organic molecules or signs of microbial life from billions of years ago, when Mars had a more hospitable climate. In addition to Mars, moons such as Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, have become key targets in the search for microbial life. Both moons have subsurface oceans beneath their icy surfaces, and there is evidence that hydrothermal activity may exist on both moons, providing the necessary conditions for life to thrive. Europa Clipper and Enceladus missions are expected to study these moons more closely in the coming years. The search for extraterrestrial intelligence, SETI. While the search for microbial life focuses on nearby planets and moons, the search for more advanced forms of life, particularly intelligent civilizations, has been the focus of the search for extraterrestrial intelligence, SETI. SETI is an ongoing scientific effort to detect signals from alien civilizations, primarily through the search for radio signals or lasers that could be emitted by technologically advanced extraterrestrials. The idea behind SETI is simple. If extraterrestrial civilizations exist and are technologically advanced, they may be sending out signals into space, either intentionally or as a byproduct of their activities. These signals could be radio waves or lasers that travel across vast distances and could be detected by us using sensitive instruments like radio telescopes. The search for extraterrestrial intelligence gained international attention in 1977 when a researcher working at the Big Ear Radio Telescope in Ohio detected an unusual radio signal that lasted for 72 seconds. The signal, dubbed the WOW signal, has never been detected again, and its origin remains a mystery. Despite the lack of follow-up detections, the WOW signal remains one of the most tantalizing pieces of evidence that we may not be alone in the universe. While the search for signals from extraterrestrial civilizations has yet to yield any definitive results, the development of more powerful telescopes such as the Square Kilometre Array, SKA, and Breakthrough Listen Initiative has led to more sensitive searches for radio signals across the sky. These efforts aim to scan the entire sky for potential signs of extraterrestrial communication. The implications of discovering extraterrestrial life. The discovery of extraterrestrial life, whether microbial or intelligent, would have profound implications for our understanding of the universe and our place in it. It would fundamentally alter our view of life, intelligence, and civilization, challenging our long-held beliefs about the uniqueness of Earth and the exceptionalism of humanity. 1. The uniqueness of life. The discovery of life beyond Earth would challenge the idea that Earth is the only place in the universe where life has emerged. It would suggest that life may be common in the universe, and that the conditions that led to life on Earth may be replicable on other planets or moons. 2. Philosophical and religious questions. The discovery of intelligent alien civilizations could raise profound philosophical and theological questions about the nature of existence, the origins of life, and humanity's place in the cosmos. It might challenge religious doctrines or lead to new interpretations of our relationship with the universe. 3. Technological and cultural exchange. The discovery of an advanced extraterrestrial civilization would open up the possibility of technological exchange. This could bring about significant advancements in science, medicine, and technology. However, it could also raise concerns about cultural differences and the potential risks of contact with a more powerful civilization. 4. The future of humanity. The discovery of extraterrestrial life could lead to a fundamental shift in how humanity views its future. The presence of other civilizations could inspire greater cooperation in space exploration or raise existential questions about the survival of humanity in the face of a vast populated universe. The Drake equation, estimating the odds of extraterrestrial life. One of the key tools used to estimate the likelihood of extraterrestrial life is the Drake equation, developed by astronomer Frank Drake in 1961. The equation is designed to estimate the number of technologically advanced civilizations in our galaxy with which we might be able to communicate. The equation takes into account several factors, including the rate of star formation in the galaxy, the fraction of stars that have planets, the number of planets that could potentially support life, the probability of life developing on those planets, and the lifespan of technological civilizations. While the Drake equation provides a framework for thinking about the number of potential civilizations in the galaxy, it is also highly speculative, as many of the values used in the equation are uncertain or based on assumptions. However, it has been instrumental in driving the search for extraterrestrial life and inspiring scientific efforts like SETI. Conclusion: the search continues. The search for extraterrestrial life is one of the most exciting and profound endeavors of modern science. Whether we are searching for microbial life on Mars or intelligent civilizations through SETI, the quest to understand whether we are alone in the universe continues to captivate humanity's imagination. As our understanding of the universe grows and our technology improves, we may one day discover that we are not alone, that life exists elsewhere in the cosmos and perhaps even in forms we cannot yet imagine. Until that day comes, the search for life beyond Earth remains one of the most important and transformative scientific quests of all time. Among the most fascinating and enigmatic objects in the universe are black holes, regions of space where gravity is so intense that nothing, not even light, can escape their grasp. These cosmic giants challenge our understanding of the laws of physics, distorting the very fabric of space-time. While black holes have captured the imagination of scientists and the general public alike, they remain some of the most mysterious and misunderstood objects in the universe. In this chapter, we will explore the nature of black holes, how they form, and the crucial role they play in shaping the structure and evolution of the universe. We will delve into the general theory of relativity, which provides the framework for understanding black holes, and look at some of the cutting-edge research that continues to uncover the secrets of these celestial objects. Finally, we will explore the profound philosophical questions that arise from the existence of black holes and their impact on our understanding of reality itself. What is a black hole? A black hole is a region of space where the gravitational pull is so strong that nothing, not even light, can escape from it. The boundary around a black hole is called the event horizon, and once an object or light passes this threshold, it is pulled inexorably towards the black hole's singularity, the point at the very center where matter is thought to be compressed to infinite density, and space-time becomes infinitely curved. The idea of a black hole arises from Albert Einstein's theory of general relativity, which describes gravity as the warping or curvature of space-time. Massive objects like stars create a distortion in space-time, and the more massive the object, the greater the curvature. A black hole represents an extreme form of this curvature, where space-time is so severely warped that it creates a point of no return, beyond which escape is impossible. Black holes come in various sizes and masses, and they are classified into different types based on their size and the type of objects they interact with. Types of black holes. Black holes can be broadly classified into three main categories. 1. Stellar black holes. These black holes form from the remnants of massive stars that have exhausted their nuclear fuel. When a massive star collapses under its own gravity, it can create a stellar black hole with a mass typically between 3 and 10 times that of the Sun. These black holes are often found in binary systems where they may pull matter from a companion star, forming a disk of material that heats up and emits X-rays. 2. Supermassive black holes. These black holes are found at the centers of most galaxies, including our own Milky Way, where a supermassive black hole called Sagittarius A resides. These black holes can have masses ranging from millions to billions of times the mass of the Sun. While the exact mechanism of their formation is still unclear, it is believed that supermassive black holes may form through the merging of smaller black holes or through the collapse of massive gas clouds. Their immense gravity plays a crucial role in shaping the dynamics of their host galaxies. 3. Intermediate black holes. These black holes fall somewhere between stellar and supermassive black holes in terms of mass. They are thought to form when smaller black holes collide or when a large cloud of gas collapses under its own gravity. Intermediate black holes are still a subject of active research, and astronomers are continuing to search for them in various regions of space. The formation of black holes. Black holes form when a massive object undergoes a gravitational collapse, a process that occurs when an object's gravity becomes so strong that it causes the object to collapse inward. In the case of stellar black holes, this occurs when a massive star reaches the end of its life and can no longer support itself against the force of its own gravity. A star's life is powered by nuclear fusion, the process by which hydrogen atoms are fused into helium, releasing enormous amounts of energy. This energy produces an outward pressure that balances the inward pull of gravity. However, when the star runs out of fuel, fusion stops, and the outward pressure is no longer able to counteract gravity. As a result, the core of the star collapses, and if the core's mass is large enough, it can create a singularity, a point of infinite density where gravity becomes so strong that not even light can escape. The event horizon, the point of no return. One of the most intriguing aspects of black holes is the concept of the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Once an object or light crosses this threshold, it is irreversibly drawn toward the singularity at the center of the black hole, where the laws of physics as we know them cease to function. The event horizon is not a physical surface, but rather a mathematical boundary that marks the point at which the escape velocity exceeds the speed of light. The event horizon is often described as the point of no return, because once crossed, there is no way for anything, including light, to escape the black hole's grasp. This makes black holes invisible. They can only be detected by their gravitational effects on nearby matter. For example, when a black hole is part of a binary system, it may pull matter from a companion star, forming an accretion disk of hot, glowing gas. The radiation emitted from this disk can be detected by telescopes, allowing scientists to infer the presence of a black hole. Singularities. The heart of a black hole. At the center of a black hole lies a singularity, a point of infinite density where matter is crushed into an infinitely small volume. The singularity is the location where the laws of physics as we currently understand them break down, and both general relativity and quantum mechanics cease to provide accurate predictions. The singularity is surrounded by the event horizon, and once anything crosses this boundary, it is inevitably drawn toward the singularity. The existence of singularities presents one of the greatest challenges in theoretical physics. According to general relativity, the singularity represents a region of space-time where the curvature becomes infinite. However, quantum mechanics suggests that matter and energy cannot be compressed into a point of infinite density. Resolving this contradiction is one of the key goals of physicists working on a theory of quantum gravity, which would unify general relativity and quantum mechanics. The role of black holes in galaxy formation. Black holes, particularly supermassive ones, play a crucial role in the formation and evolution of galaxies. It is thought that supermassive black holes are found at the centers of most galaxies, and their gravitational pull can influence the orbits of stars, gas, and dust within the galaxy. Some scientists believe that the growth and behavior of these black holes may be directly tied to the formation of galaxies themselves. In fact, the relationship between galaxies and their central supermassive black holes appears to be mutually reinforcing. As black holes grow by accreting gas from their surroundings, they can release vast amounts of energy, which can have a profound effect on the galaxy. This process, known as active galactic nuclei, AGN, can create powerful jets of particles and radiation which can influence the surrounding galaxy and its star formation. The energy emitted by supermassive black holes may also regulate the rate of star formation in their host galaxies. Some researchers believe that these black holes can act as cosmic feedback mechanisms, blowing away gas and dust and preventing further star formation. In this way, black holes could play an essential role in the evolution of galaxies, influencing both their structure and the number of stars they contain. Time and space. Near a black hole. One of the most fascinating aspects of black holes is their ability to warp space and time. According to Einstein's theory of general relativity, mass and energy cause space-time to curve, and the more massive an object, the greater its curvature. Black holes represent the most extreme example of this curvature, where space-time becomes so warped that it forms a singularity at the center. Near a black hole, the effects of gravity are so intense that they cause gravitational time dilation, a phenomenon in which time appears to slow down relative to an observer far from the black hole. If you were to approach a black hole, time would appear to pass more slowly for you compared to someone farther away from the black hole. At the event horizon, time would effectively come to a standstill from the perspective of an outside observer, although to someone falling into the black hole, time would pass normally. This warping of space-time around a black hole also leads to the phenomenon of spaghettification. As an object approaches a black hole, the difference in gravitational pull between the parts of the object closer to the black hole and those farther away becomes so great that it stretches the object into a long, thin shape, much like spaghetti. This stretching effect is caused by the intense tidal forces near the black hole and is one of the most dramatic consequences of a black hole's gravity. Black holes and the end of the universe. Black holes may also play a crucial role in the ultimate fate of the universe. As stars burn out and galaxies eventually merge or fade away, black holes may become the last remaining objects in the universe. Over incredibly long timescales, black holes will lose mass through Hawking radiation, a process predicted by physicist Stephen Hawking in 1974. According to Hawking's theory, black holes slowly radiate energy and lose mass over time due to quantum effects near the event horizon. This radiation, known as Hawking radiation, causes black holes to evaporate gradually, eventually leading to their disappearance. While the process is incredibly slow for large black holes, taking trillions of years, it suggests that black holes may not be permanent fixtures in the universe. As black holes slowly evaporate, the universe will continue to cool and expand, eventually reaching a state of maximum entropy in which all processes cease. This scenario is known as the heat death of the universe, where black holes, the last remnants of matter and energy, will evaporate and disappear, leaving behind a cold, dark, and lifeless cosmos. Conclusion. The enduring mystery of black holes. Black holes remain one of the most mysterious and intriguing phenomena in the universe. From their formation in the collapse of massive stars to their role in shaping galaxies and space-time, black holes continue to challenge our understanding of physics and reality. Despite the groundbreaking work done by physicists, much about black holes remains elusive. As we continue to study these cosmic giants, we gain deeper insights into the fundamental laws of the universe. The more we learn about black holes, the more we realize just how much they can teach us about the nature of space, time, and the ultimate fate of the cosmos. As we journey further into the mysteries of the universe, we encounter two of the most elusive and fundamental forces in cosmology: dark matter and dark energy. Together, these invisible entities make up 95% of the universe's total mass and energy, yet we know little about their true nature. While we have a firm grasp on the forces we can observe, such as gravity, electromagnetism, and the strong and weak nuclear forces, dark matter and dark energy remain hidden in the shadows of the cosmos, shaping the universe in ways we are only beginning to understand. In this chapter, we will explore the nature of dark matter and dark energy, how they influence the structure and expansion of the universe, and the ongoing efforts to detect and study these mysterious forces. We will also look at some of the theories that attempt to explain their existence and role in the cosmos. What is dark matter? Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to current instruments that rely on electromagnetic radiation, such as visible light, radio waves, and X-rays. Despite being invisible, dark matter's existence has been inferred through its gravitational effects on visible matter. In other words, although dark matter does not interact with light or other forms of electromagnetic radiation, it interacts with regular matter through gravity, and its presence is felt through its gravitational pull on galaxies and galaxy clusters. The concept of dark matter was first proposed in the 1930s by astronomer Fritz Zwicky after he observed the motion of galaxies within a galaxy cluster. He noticed that the galaxies were moving much faster than expected based on the amount of visible matter in the cluster. He concluded that there must be a large amount of unseen matter exerting additional gravitational pull on the galaxies. This unseen matter, which Zwicky called dark matter, became the subject of intense study in the following decades. Today, dark matter is believed to account for about 27% of the universe's total mass and energy. It plays a crucial role in the formation of galaxies and the structure of the cosmos. Without dark matter, galaxies would not have enough mass to hold together and would fly apart under their own gravitational forces. Evidence for dark matter. While dark matter has never been directly observed, there is a wealth of indirect evidence that supports its existence. Some of the key pieces of evidence include galaxy rotation, curves. One of the most compelling pieces of evidence for dark matter comes from the rotation curves of galaxies. In the 1970s, astronomer Vera Rubin observed that the outer regions of galaxies were rotating much faster than expected based on the amount of visible matter in the galaxy. According to Newtonian physics, the outer stars in a galaxy should orbit more slowly than those near the center, where the mass is concentrated. However, Rubin's observations showed that the stars in the outer parts of galaxies were moving at roughly the same speed as those closer to the center. This suggested that there was a large amount of unseen mass, dark matter, providing the gravitational pull necessary to keep the galaxies from flying apart. Gravitational lensing. Another key piece of evidence for dark matter comes from the phenomenon of gravitational lensing, which occurs when the gravitational field of a massive object bends the light from a more distant object. According to Einstein's general theory of relativity, massive objects warp the fabric of space-time, and light traveling through this warped space will follow a curved path. This effect has been observed around galaxy clusters, where the amount of bending suggests that there is much more mass present than is visible, implying the presence of dark matter. Galaxy clusters. The Bullet cluster, a pair of colliding galaxy clusters, provides another strong piece of evidence for dark matter. When these clusters collided, the visible matter in the form of hot gas was slowed down by the collision, while the gravitational influence, and thus the mass of the clusters, remained separated. This observation suggests that most of the mass in galaxy clusters is not in the form of visible matter, but in the form of invisible dark matter, which does not interact with the gas but exerts gravitational pull. What is dark energy? If dark matter is the invisible substance that holds galaxies and clusters together, dark energy is the mysterious force that is pushing the universe apart. Dark energy is thought to make up about 68% of the universe's total energy density and is responsible for the accelerated expansion of the universe. The existence of dark energy was first proposed in 1998 when two independent teams of astronomers discovered that the expansion of the universe was accelerating rather than slowing down, as was previously believed. This discovery was based on the observation of distant supernovae, which appeared to be farther away than expected. In order to explain this accelerated expansion, scientists proposed the existence of a repulsive force, dark energy, that counteracts the gravitational pull of matter and causes the universe to expand at an ever-increasing rate. Dark energy is thought to have a constant negative pressure that causes space itself to stretch. Unlike matter, which exerts attractive gravitational forces, dark energy repels matter, driving the accelerated expansion of the universe. While the exact nature of dark energy remains a mystery, its existence has profound implications for the ultimate fate of the cosmos, the role of dark matter and dark energy in the evolution of the universe. Dark matter and dark energy play critical roles in the structure and evolution of the universe. Without dark matter, galaxies would not have been able to form in the first place. Dark matter acts as a kind of cosmic scaffolding, pulling matter together and helping to create the galactic clusters and cosmic web that form the large-scale structure of the universe. On the other hand, dark energy is responsible for the accelerated expansion of the universe, pushing galaxies farther apart as time goes on. This accelerated expansion is causing the universe to stretch out at an ever-increasing rate, and some scientists believe that this expansion will continue indefinitely, leading to the heat death of the universe, a state of maximum entropy in which all stars burn out and the universe becomes cold and dark. The interplay between dark matter and dark energy will shape the future of the universe. If dark energy continues to dominate, it could lead to a big freeze in which galaxies, stars, and eventually atoms themselves are stretched apart by the expansion of space. If dark matter somehow overcomes the effects of dark energy, the universe could eventually collapse in a big crunch, where galaxies and stars are drawn back together into a singularity. The quest to detect dark matter and dark energy. Despite the overwhelming evidence for the existence of dark matter and dark energy, scientists still do not know what these mysterious forces are made of. Understanding their true nature is one of the greatest challenges in modern cosmology, and it has prompted a number of experiments and observational programs aimed at detecting dark matter and dark energy. Direct detection of dark matter. Scientists are working on a variety of methods to directly detect dark matter particles, which are thought to be weakly interacting massive particles, WIMPs. One approach involves building underground detectors that are sensitive to the rare interactions between WIMPs and regular matter. The LX-Zeppelin experiment and the Xenon 1T experiment are two such efforts, both located deep underground to shield them from interference by cosmic rays. While no dark matter particles have been detected yet, these experiments continue to improve and push the limits of detection. Observations of dark energy. The study of dark energy is primarily done through the observation of the expansion of the universe. One of the most important tools for studying dark energy is the observation of supernovae. By measuring the brightness and redshift of distant supernovae, scientists can determine how fast the universe is expanding at different points in time. Another method involves mapping the distribution of galaxies across the sky and studying the large-scale structure of the universe to see how it has evolved over time. In addition to these methods, the European Space Agency's Euclid mission and the NASA's James Webb Space Telescope will provide powerful new data on the properties of dark energy and how it affects the evolution of the universe. These upcoming missions promise to bring us closer to understanding the true nature of dark energy. Conclusion: the invisible forces shaping the cosmos. Dark matter and dark energy are two of the most profound and mysterious forces in the universe. Together, they make up the vast majority of the universe's mass and energy, yet we can't directly observe them. Their presence is inferred only through their gravitational effects on visible matter and the expansion of space itself. Despite the challenges in detecting them, dark matter and dark energy are central to our understanding of the cosmos and its future. As research continues, and as our observational tools become more advanced, we may one day uncover the true nature of these hidden forces. Until then, dark matter and dark energy remain key pieces in the puzzle of the universe's structure, evolution, and ultimate fate. As we approach the final chapter of our journey through the cosmos, we arrive at one of the most profound and speculative questions in modern cosmology. What is the ultimate fate of the universe? The story of the universe began with the Big Bang, a singular event that set the stage for everything that followed. But just as the universe had a beginning, it is also destined to have an end. The question is, what form will that end take? Throughout this chapter, we will explore the different theories and possibilities for the end of the universe. From the Big Freeze to the Big Rip to the possibility of a Big Crunch, we will examine the various scenarios that cosmologists propose for the universe's future. We will also explore the role of dark energy, dark matter, and the expansion of space-time in shaping the ultimate fate of the cosmos, and what these events could mean for the future of time itself. The fate of the universe. A cold, dark, and lifeless future. The most widely accepted theory about the end of the universe is the Big Freeze, sometimes called the heat death of the universe. This scenario predicts that as the universe continues to expand, it will eventually reach a state of maximum entropy. Entropy is the measure of disorder or randomness in a system, and as the universe expands, energy will become more evenly distributed, leading to a state where no useful energy remains to power stars or sustain life. The Big Freeze is predicated on the ongoing expansion of the universe, which is driven by the mysterious force of dark energy. As dark energy continues to accelerate the expansion, galaxies will drift farther and farther apart. Eventually, stars will run out of fuel and burn out, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. Over time, even black holes will evaporate due to Hawking radiation, and all that will remain is a dark, cold, and empty universe. In this scenario, the universe will experience a slow fade to black, with no stars, no light, and no active processes. The end of time as we understand it could occur in a universe where all matter and energy have been evenly distributed and no further work can be done. It would be an era of complete stagnation where nothing new can occur, and the universe continues to expand in a state of perfect equilibrium. The Big Rip, a violent end to the cosmos. While the Big Freeze offers a picture of a gradual, almost serene end, another possibility is a much more violent conclusion to the universe's story, the Big Rip. The Big Rip is a scenario in which the expansion of the universe accelerates to the point where dark energy becomes so powerful that it overcomes the gravitational forces binding galaxies, stars, and even atoms together. In the Big Rip scenario, dark energy's repulsive force would grow stronger over time, eventually tearing apart the galaxies, solar systems, and stars. As the expansion continues to accelerate, galaxies would be ripped apart, and stars would be torn from their orbits. Finally, the force of dark energy would tear apart the very fabric of space-time, ripping atoms and subatomic particles apart, leaving behind a universe that is completely fragmented. The timing of the Big Rip depends on the nature of dark energy and how it evolves. If dark energy continues to grow stronger, the universe could experience this catastrophic end in a few billion years. The exact details of the Big Rip remain speculative, but it presents the possibility of a dramatic and violent end to existence, a universe torn apart at its very seams. The Big Crunch, a universe reversed. In contrast to the Big Freeze and the Big Rip, the Big Crunch offers a more cyclic view of the universe's fate. The Big Crunch theory suggests that the universe could eventually stop expanding and begin contracting, eventually collapsing back into a singularity, a point of infinite density. This theory proposes that gravity, which is currently being counteracted by dark energy's repulsive force, could eventually overcome the effects of dark energy and cause the universe to collapse in on itself. The Big Crunch would begin when the expansion of the universe slows down, potentially due to a weakening of dark energy or the eventual dominance of gravity. As galaxies, stars, and planets are drawn toward each other, the universe would become increasingly dense and hot. Eventually, everything would collapse into a singularity, much like the state of the universe at the time of the Big Bang. In this model, the universe would undergo a reversal of the Big Bang, a contraction instead of an expansion. The ultimate end would be a complete collapse of space-time into a dense, hot point, possibly leading to another Big Bang and the beginning of a new cycle. The Big Crunch theory suggests that the universe may not have a single irreversible end, but could be part of an eternal cycle of birth and death. The role of dark matter and dark energy in the universe's fate. Both dark matter and dark energy play key roles in determining the ultimate fate of the universe. Dark matter, which accounts for about 27% of the universe's mass, is responsible for providing the gravitational pull necessary to hold galaxies together. Without dark matter, galaxies would not have enough mass to stay intact, and the structure of the universe would be vastly different. However, dark energy, which makes up 68% of the universe, is causing the accelerated expansion of the universe. Dark energy's repulsive force is driving galaxies away from each other at an ever-increasing rate. This force is the dominant factor in scenarios like the Big Freeze and the Big Rip, where the expansion of the universe continues indefinitely. In the case of the Big Crunch, dark energy would have to weaken or be overcome by gravity in order for the universe to collapse. If dark energy remains constant, it would likely lead to a Big Freeze. If dark energy evolves or reverses its effect, gravity could eventually dominate, causing a contraction and a Big Crunch. The heat death, the end of all thermodynamic processes. The most widely accepted theory for the ultimate fate of the universe is heat death, or maximum entropy. In thermodynamics, entropy refers to the level of disorder or randomness in a system. As the universe expands and stars burn out, the total energy in the universe will become more evenly distributed, leading to a state of maximum entropy where there are no gradients of energy left to fuel any processes. In this state, there would be no thermodynamic processes occurring, no stars burning, no energy being used to do work. The universe would enter a state of complete thermodynamic equilibrium, in which every part of the universe is equally cold and devoid of usable energy. This scenario would mark the end of all physical processes and would be the most somber and still conclusion for the universe. The philosophical implications of the end of the universe. The potential endings of the universe, whether through the Big Freeze, Big Rip, or Big Crunch, raise profound philosophical and existential questions about time, space, and the nature of existence itself. If the universe is destined to end in one of these ways, what does it mean for our place within it? Does the eventual death of the universe imply that all meaning and purpose are ultimately impermanent, or does it suggest that the cosmos, in some form, could be reborn through cycles of destruction and creation? The study of the universe's ultimate fate forces us to confront the limits of our understanding and the possibility that the cosmos may be far more transient and cyclical than we ever imagined. It reminds us that everything we know, from the stars in the sky to the lives we lead, is part of an impermanent system that is constantly evolving and, eventually, decaying. The search for answers to these questions not only drives cosmological research, but also encourages deep reflection on the nature of existence, the passage of time, and the inevitability of change. Conclusion: the endless journey of the universe. The future of the universe remains uncertain, with several possible scenarios for its ultimate fate. Whether the universe continues expanding until it becomes a cold, dark expanse, or whether it collapses back into a singularity for a new cycle, the story of the universe is far from over. The very nature of cosmic time and space suggests that the universe may be far more dynamic and complex than we can fully comprehend. As we continue to observe the cosmos and develop new theories, we are reminded of the impermanence of all things, yet also of the infinite possibilities that exist within the vast expanse of space and time. The future of the universe remains a mystery, but it is a mystery that continues to inspire scientists, philosophers, and dreamers to look toward the stars, ever curious about the universe's unfolding story.